Good morning, everyone. Any question? Okay, so if you remember in the last class, we just did this part on the chapter 13, and we finished all these questions, how to find out the studentized residuals and Cook's D. So I will upload the solutions later on. Let's consider another data set. I uploaded this data set in ELC. If you go to the ELC and download this data, Palm Beach data set. Okay. And open this in JUMP. So this is the data set. It was in the election, in presidential election in US in 2000. So we have in Florida, we have the different county and two different candidates. One is the Bush, another one is Buchanan. Okay, now, first we'd like to look at the relationship between the number of votes that Bush got and Buchanan got. And then we can look at this scatter plot, and then we would like to know whether there is any unusual observation in this data set or not, finding out the Cook's D or studentized residuals or standardized residuals and fit the models. So the question is very simple. We'd like to fit the models here based on this. So if you go back to the question will be like this. I didn't put the questions, but the questions that I would like to see, that we'd like to draw a scatter plot of the number of votes that Buchanan received against the number of votes that Bush received, and write down the least square regression equation and include the graph. So let me do this part here. So we fit the models. Very simple models here. The Bush versus the Buchanan. Okay. And these are the counties there for each county. And we fit these models, a simple linear regression models. Okay, when we fit this model, what can we see here? Can anyone tell me? From these models. So it's looks like a non-linear pattern. There are two outliers, Raphael said yes. Okay, now if we look at these scatter plots here, residual plots, we can see that there are extreme points in the lower end here, one upper end here, and we have small values of residual for the smaller values of x, but for the larger values of x, the residuals is getting larger. Okay. Now, but we can still see that there is a significant relationship between the number of votes that Buchanan got and the vote drop. But the pattern looks like that linear model is not a good model here. Okay. Now, I would like to identify these 2 points in the data set that you say that this is an outlier. So how can I identify these 2 points here? So here is the 1 point. You can draw the box and you can see here they highlighted this point. Similarly, if you draw a box here, you can see that highlighted another point here, the Palm Beach. So we have 2, one is the Dade County, another one is the Palm Beach. Okay. Now the Palm Beach County, we can see that number of votes here, the Bush got this and the Buchanan got this, which is much higher compared to the other counties where the Buchanan vote is less. And the another one that we have seen in the Dade County here, the Bush got high number of votes compared to the Buchanan. Now, We just observe these two as an outliers. But how can we know exactly that how large these values are? So what can we do? We can look at our studentized residuals or the standardized residuals and Cook's D or head values. So calculate studentized residuals, yes. So how can we calculate the studentized residuals? Okay, so we need to go to the shape columns. We know that this is what we know, that studentized residuals directly can be get, but studentized deleted residuals you have to calculate it. Now we can get the residual values here. We can get the head values here. We can look at the Cook's D here directly. Now, based on the Cook's D, from the Palm Beach County, if you look at the Palm Beach County, what is the Cook's D here? It's very high, 63. Okay, now what about Dade County that we selected here? 0.27. Okay, now if we look at the other values are very small compared to these two, and we have another one, Pasco, which is the Cook's D is higher. Now what about the H values, which is called the head values? So for the Dade County, if we already know that Dade County here, 0.02. Now it's not so high, but if you look at the Palm Beach County, this is very high. Okay, let me see what he said. St. John's 2. The Cook's D is high, but if you look at the H values, that's not so high. No, it's not high. You can see e to the power minus 6. That means it's very small. It's not high. E to the power minus 6 means 0.00000050 before 8. So this is small values. It's not large. And this one is also Pasco. I was reading, misread it because this is also very small. So only large values for the Cook's D is the Palm Beach one. And the second largest one, we can see the Dade County here. So these two are the two largest values here. Cook's D. And this. So we already identified that, okay, these are the two values that are the unusual values in our scatter plots here, as well as if we look at these residual plots. Okay. Now, what else we can look for this? Now, I would like to know, if we delete this observation and refit the models, what happens to this relationship? We still know that this is here, they have a significant relationship because the p-value is small, and you can see that the parameter estimates and the effect test is significant. But do we see any changes in the slope? Can we use Cook's D or studentized residuals? Like there are two different methods for the same outcome. Yeah. So for the Cook's D, here if you remember what I said, if you go back to the chapter 13. What is the chapter 13? So this is what we use for detecting outliers. Okay, so the leverage points, H calories can tell us these are the head values for the leverage points. Now when we look at the studentized deleted residuals, that's like the different criterion And then we also looked at the Cook's D here. So would omission of the point dramatically affects the prediction? Then we get an idea by looking at the measure of Cook's D, and dump will compute for us automatically. And we see that biggest studentized residuals will have larger Cook's D. So Cook's D indicate that we have very different model estimates when the observation is included or when it is not included in the estimation process. That's why I showed you here the Cook's D. Now, I want to show you that, okay, if I don't include this point, whether we get a different estimates and a different parameter estimates for this one. So look at this now. First of all, if you look at your R square is 38% here. Our parameter estimates is 79.10. Now, with including, because which one has the largest Cook's D? If you go back to this data set, we can see here the Palm Beach County, the Cook's D is very large compared to the Dade County. So let's remove these points from this data set and refit the models and then look how we can increase this. Okay, so I delete this rows because we identify this as the largest Cook's D. Okay. Now refit the models using the rest of this data set. Now, what happens to the residual plot now? Sorry, scatter plot. So we can see the different change now. So what changes you can see now? We can say that, okay, linear models might look good for us here. The fitting the linear models is not bad. Now, residual plots are, you can see that they are randomly scattered around the zero line. Okay. Now what about our R square? You can see a dramatic change in the R square. What is R square now? 86%. Before this, when we include this Palm Beach County, our R square was only 38%. But after excluding these Palm Beach County values, which is here, this one, the one that we identified here, this is a large Cook's D, and this gives us here this point that we identified here. Actually, this point is not in this data set, we already deleted, so you cannot see here. Now, this is what we can see, the dramatic change in the R square. Also, if we look at the scatter plot and as well as the residual plot, we can see that now it's reasonable to assume that there is a linear relationship between these two variables. We can see that a dramatic change in our residual plots. We can see our R square is very high. Look at the error sum squares here. This is our error sum squares here. Look at the error sum square here, which is very high. Sorry. So E plus 11. Now E plus 10, little bit smaller, it's not reduced, but if you look at your F ratio here, 403, and this one was only 41. So we have high power of detecting whether there is a relationship, and if there is no changing the parameter estimates, but we can see F ratio changes a lot and R square changes a lot if you remove these points. So these points like Cook's D can tell us whether it's reasonable to remove these points from this data set, and this is what I mean by using the Cook's D. Would omission of the point dramatically affect the predictions? So this is what we look at the Cook's D. So that is, has it dramatically impacted our parameter estimates, our model, and therefore our prediction and inference? We can get an idea by looking at a measure of called the Cook's D. Now, if we remove the other one, the Dade County, because we have seen that Dade County here, where is the Dade County? It's remove both of these, I think. Date and the Coxley both. Because both are selected, so I removed the date county as well. Now if I go back and undo this, so the date county is there, Palm Beach is there. So let's remove only the Palm Beach one. That's the date county one. So keep the date county as it is, just remove the Palm Beach one. So we have now 66 observation, date county is here. Now repeat these models. Previous one we remove both of these, date county and the Palm Beach, because both of them are selected. So when I remove this, remove both. So still we can see that a dramatic change in the slope. So if you look at this slope here, so this is our slope here, and we can see that the points are looks like a non-linear pattern, but when we just remove the date county, we can see that there is a linear pattern, okay, because this line influences a lot. Now these points here, what is this point actually called? Now there are 2 points, if you remember, if you go back here, the previous plot, this one. There was 2 points. One, we have large x values. The other one, we have large y values. So what we call these 2 values? Do you remember what we call actually? If we have large x values and the large y values. That's very important. I can give you some situations and tell you fit the models and then look at these points. So we know that there are 2 things that you have to keep in mind. That's very important. When we discussed about this, if the value of our predictor is unusual, we call it the Leverage point. If the value of the response is unusual, we call it this is an outlier. Now does the observation distort or have an undue influence on the overall regression models? Now look at these 2 points. If you look at these points here, what is this point here? This is, we have large x values. Y value is not so large. What about this one? We have large y values, but x value is not so. So when we have large x values and it has an influence on the slope, we call it the influential observations. Otherwise we usually call it the leverage point. When we have large y values, we call it this is an outlier. Now leverage point is called the influential observation if it changes the slope a lot. Now after removing this point, if you look at here, we just remove this point, you can see that a dramatic change in the slope. The slope changes a lot. Now we can see here the slope is now 215, okay. Error is this one, our f is this one. Now look at this, when we feed the models with these values, our slope was only 79. Okay? Is that clear? Now it changes a lot. The slope changes a lot. So this implies that this is an influential observation because this affects the slope. Is that clear? And you know what is the slope means. So if you look at this, when we fit the models including this Palm Beach County, so this the large x values, we get our slope is 79.10. Now when we fit the models excluding this point, you can see a dramatic change in the slope, as well as we have R square is higher, our f value is higher. Now when we remove both of these, this is what we did it here, we can see that the slope changes definitely when we remove both of these. And also we can see that f value is very large because this is, we remove outliers as well as the influential observations. But when we just remove the influential observation, you can see the slope was changing a lot. So this point is called the influential observations. And the Cook's D, because this one has a large Cook's D compared to all other values. And what is large Cook's D means, I said here, so here I said that a large Cook's D indicate we have very different model estimates when that observation is included and when it is not included in the model estimation process. So it is an argument that the observation is highly influential point, particularly if it has both high leverage and high error. Generally speaking, a Cook's D worth investigating one is that is higher than 1 or 2. So in our case, we can see that Palm Beach County has a large Cook's D, which is 63. Now, after including this one or excluding this value, we can see a dramatic change in our model estimation process. That means parameter estimates, R square, and F values. Is that clear from these questions, what I was looking for? Okay. Now, we can also see that now after excluding both of these, now we can see that model assumptions is good. Now if you look at the residual plot, or if we feed the normal quantile plot, we can see whether they are normally distributed or not. Okay, so this is what we have here. And then you can just do the normal quantile plot. You know how to do it. So the main message from this data analysis part, I want to show you, if we have a large X values, we don't necessarily need to tell that this is an influential observation unless it has large Cook's D. And if we remove this point from the data set, and if we see that there is a dramatic change in the parameter estimates, R square value and the F value, then we can say that this is a influential observations. But not necessarily that, so it will always be an influential observation. It can be a leverage point, large X values, but if it's not affecting the slope a lot, so we don't need to tell that this is an influential observations. Okay, so that's the summary of this chapter. So I uploaded this data. Maybe I'll upload some questions related to these Palm Beach counties, and then I'll ask you to do this on the data analysis that I just showed you. Okay, if you don't have any questions, then let's start with the new chapter. So this is we call it the logistic regression. So what is the difference between the logistic regression and the multiple regression or the simple regression so far we learned, or ANOVA or ANCOVA? Now, so far we consider that our response variable is continuous. Now in multiple regression we consider that, okay, our response variable is continuous as well as our predictors are continuous. So we have more than one predictor. This is the multiple regression. Now in ANOVA we say that, okay, we have our response variable is continuous and we would like to know the effects of the categorical variables on the response variables. So instead of saying that for one unit increase, we can just say in ANOVA that, okay, if we change the levels of the categorical variables, what is the average change or the group change in the response variable? So we compare the means for the different groups. What we did in ANCOVA, our target is to know the effects of the categorical variables on the response variables, but we want to adjust the effects of some continuous variables. But we don't consider this as a predictor, we just consider it as a covariate, and we want to adjust the effects of this covariate and see the relationship between the response variables and the categorical variables. But all the cases, our response variable was continuous. And we know that always the assumption for the multiple regression models or the ANOVA or the ANCOVA, our assumption, one of the assumptions is that error term is normally distributed. Okay? So this is one of the assumptions. And all the response variables are quantitative. But now we extend this idea, and then we are saying, what happens if our response variable is not quantitative? It's a categorical variable. So in this case, you cannot use ANOVA, ANCOVA, or multiple regression model. So we have to go back to another technique, we call it the logistic regressions. So the logistic regressions tells us whether we can say that our response in this category or the other category. So in this case, our normality assumption is not valid here. So we cannot assume the error term is normally distributed because our response variable is not continuous. So when we have a categorical predictor, this is often not an unreasonable assumption, but when we have response variable that is not continuous, so we don't assume this. Now, in this chapter, we will limit our situation that when we have quantitative predictors, but our response variable is binary. So binary means either success or failure or yes or no. There are many situations. Now, what is the goal of this analysis here? We would like to see whether the levels of the predictor can be used to predict a categorical outcome. So can you use the values of the predictor to predict the value of the categorical outcome? Because we cannot estimate it like in usual situations where we have the response variable is continuous. So now it's a categorical. So we just want to know the categorical outcomes. Now there are many examples of like this. Suppose if you know a person's ability in a given domain, and you want to know that, use that knowledge to predict whether that person gets an item on a test on the right or wrong. So we'd like to use the person knowledge to predict whether the person can get an questions or an item in the exam right or wrong. What is the chance the person will get this answer right, given that he has this knowledge? So this is what we'd like to predict here. So based on the levels of the categorical variables. Now, another examples, like we have many situations, like if you know a person's total years of education, you might want to show if that is a useful predictor of political party in a two-party system, whether they will be in this party or the other party. Or if you want to know the dose of a drug, is a useful predictor of whether the patient is cured after given a time. So we'd like to know whether the patient is cured or not, given that we give the dose, which is a quantitative variable. Or we can say that we'd like to know the effect of age, or we can say is the age of the patient is a useful predictor to predict whether the patient has a coronary heart disease or not. So you can see always our response variables in this case is a dichotomous one. So we are saying either yes or no. So we can say yes is 1, no is 0. Now we are using X here, the continuous predictor. So we are just considering one predictor. If we consider one predictor, so this is called simple logistic regression. Like as in the multiple linear regression and the simple linear regression, only difference is that if we have only one predictor, this is a simple linear regression. If we have multiple predictors, so we call it the multiple linear regression. So here if we consider only one predictor, this is called simple logistic regression. But if we include more predictors, then it will be multiple linear regression, multiple logistic regressions. Now, we are only considering two levels or the two categories of the response variables, either yes or no or success or failures, whatever we want. Okay. Any questions so far? Do you get the idea of this, what we are talking about here? Now, so all these are examples of the problems when we have a categorical predictors when we have a quantitative predictors and the categorical response. Because these responses are binomials of two categories, so we have some few problems. So what is the problems here? We cannot write our simple models in this form, that they are linearly related. We cannot say that yi equal to beta 0 plus epsilon I, which is our compact model, and error terms are not normally distributed because the response itself is not normal. So we cannot use the model form like this that we are already using in other cases. Now we cannot write in this form. So what is the idea? What we can do or how we can write our models? So all these examples we are trying to predict that there is some value of the predictor for which the response variables reliably from one category to the other category and stays there. So if this is the case, you have an association between the two variables. So let's look at the data set that I uploaded in ELC. We call it the Logix data set. So I will explain what this data set tells us. So if you go to the ELC, you can see here is the data set, the Logix one. So download this data and open this data in JUMP. So in this data, we'd like to know or predict that whether a person will subscribe to a newspaper based on their ages. So here you can see we'd like to predict whether a person subscribes to a newspaper based on their age. So subscriber here, these variables, if you look at these variables, this is a categorical variables of two categories, either they will subscribe which is 0 or other they will not subscribe which is 0 and 1 they will subscribe. And we'd like to predict whether a person will subscribe to a newspaper based on their ages. So age is a continuous predictor. Now, this is a categorical predictor, but since we have coded like 0 and 1, so we can just change this one as a numeric, considering as a numeric, but it's a categorical predictors. Categorical response variables. Now feed the models. Okay. Now if you feed the models here, feed y by x or whatever you want. Maybe just fit y by x is nice because you don't want to see any other things. So subscribe is our response variables and age is our predictors. Now if you look at this, what can we see? We can see that all the points are clustered around the two levels of these response variables. One is 0 and another one at the level 1. What can we see? Do you see anything in this plot? Can anyone tell me? Okay, now what is this age? Age is, we know that this age is a continuous variables, and 0 means whether they will subscribe to a newspaper. 1 means, sorry, whether they are not subscribing a newspaper. 1 means they subscribe to a newspaper. Now you can see that when the age is older, so there is high chance of the people who subscribe to a newspaper. Younger age people is less chance to subscribe to a newspaper. So this is what we can see, that depending on the age, okay, more subscription for ages more than 40. Yes, this is what I was talking. Thank you, Priyanka. Now we can see that when the people get older, there are higher chance of subscribing to a newspaper. Okay, now if you go back, we can see that we are trying to predict whether someone subscribed to a newspaper by using their age as the explanatory variables. And we looked at this one, and we can see here the younger people tend not to subscribe, while the older people tend to subscribe. But we still have the problem of mathematically representing this model. It would be nice to get something out of this form. But the question is that, can we write this model in this form? Since our response variable is not continuous, so we cannot write the model in the linear form like this that we are using earlier. So let's think, if we don't have a predictor and we are just instead interested in the response, that means we want to know what is the chance of subscribing to a newspaper. So what is the chance that the response y equal to, for example, if we say y is the response, what is the chance they will subscribe to a newspaper? That means y equal to 1. So what is the probability that y equal to 1? Now, whenever we have a categorical response, we have dealt with the probabilities. So we'll do this here again in the next chapter, the contingency table. But now we would like to look at or know that the probability that someone subscribe depends on their age. So here what you would like to know, we would like to know what is the probability that someone will subscribe to a newspaper or not depending on their age. So we'd like to predict the categorical response variables, though basically we'd like to predict whether there's someone will subscribe to a newspaper. This is a success, or we can say yes or 1 based on their age. Now, if we reconsider our data, instead of success and failure as probabilities, specifically that is in our examples, we would like to model the probability that someone subscribes as our response, and the probability that according to this plot that we would increase as age increases. So we can see here, if we look at this, if we fit the models here, so we can see that if age is increasing here, the chance of subscribing to a newspaper is increasing here. For older age people are subscribing to a more newspaper. Now, how can we fit the models and look at this? Now, one way, if we just fit a linear models, and the problem is that the lines are unbounded, so we go in both directions, but we know that if we would like to find out the probability is always between 0 to 1. We cannot go beyond 0 or above beyond 1. So if we fit the linear models here, in this case, for examples, what we can see, fit the line. So we can see that it goes below 0 here. Okay. So is this a good fit? Because we know that the probabilities cannot go beyond 0 or above 1. But we can see if we fit the linear models here, this is beyond zeros. So how can you overcome these situations in this case? So we cannot fit the linear models that we are usually doing in earlier cases. So that's the situation we use a transformations. And this transformation is called the logit transformations. And if you remember in chapter 13, if you go back, at the end of the chapter 13, I told you, certain types of data have generally accepted transformation that will bring them in line with our assumptions. So if we have the proportions, or like the response variable is categorical, so the best transformation for this type of the proportion means it's between 0 and 1. So in this case we know that our response is between 0 and 1 because we have what is the chance that someone subscribed to a newspaper. So the probability cannot be beyond 1 or beyond 0 in lower end. So in this case the best transformation is called the logit. So what is the logit? So we take the natural log of the response variable. So we call it, this is an odd. So odd of y divided by 1 minus y. So this is called the odd, and we take the natural log of this. So this transformation is called the logit transformations. So we are going to use these transformations here. We cannot fit the linear models because the linear models violate the condition that the probability should be between 0 and 1. So please stop me if you have any questions. Now, I said that recall the logit transformation if our response is probabilities. Probabilities means the proportions, the same thing between 0 and 1. So here we say that yi, we denote it by pi I, which is the probability of success or group membership for the ith observation. And the logit of this response is log of pi, which is log of y, is ln pi divided by 1 minus pi. Now, this part is called the odds, and the whole thing is called the log odds of the success, or we call it the log odds or log odds of success. Now we transform this into the form of the logit, and then we fit the models using this logit transformation. So now this is no longer a linear form that we consider yi equal to beta 0 plus beta 1 xi. Instead of yi, now we are using the log of yi divided by 1 minus yi, and we are transforming this, and then we put these linear models in the transform form, not the original form. And why I use the transform form, you have seen that when you fit the linear model based on the original form, we can see that it violates the condition that the probability or the proportion should be between 0 and 1. So we can't see it is in between 0 and 1. So 1, usually in JAMP they consider 1 is the success. By default, the lowest value by default they consider is the reference category. Now you can change the reference categories by using the value ordering the column properties and reverse the order. Now this inverse logit on both sides, if we take so now you can see that if we take the logarithm on both sides, so we can say that pi I will be equal to, how we can get this pi I equal to in this form? Based on this one. Now look at this. So we are saying that pi I equal to e to the power beta 0 plus beta 1 xi divided by 1 plus e to the power beta 0 plus beta 1 xi. look at this situation, how we get this one, we get it from this part. Now we know that logit of pi I is equal to, so we can say ln pi divided by 1 minus pi is equal to beta 0 plus beta 1 xi. Is that clear? We just plug in this on here. Now if we just want to find out pi 1 minus pi, so it will be e to the power beta 0 plus beta 1 xi. Now I want to find out the pi values, and then pi value is this one. Is that clear how I got this one? So now if you cross multiply here, the pi will be equal to e to the power beta 0 plus beta 1 xi minus pi times e to the power beta 0 plus beta 1 xi. Now if you take this into other side, then we can see that it will be 1 plus e to the power beta 0 plus beta 1 xi times pi. And then we divide it by this. So this is a simple calculation. So you can say pi plus pi times e to the power beta 0 plus beta 1 xi equal to e to the power beta 0 plus beta 1 xi. Now if you take the pi common, so we can say 1 plus e to the power beta 0 plus beta 1 xi is equal to e to the power beta 0 plus beta 1 xi. And then pi will be equal to this form that we just say, e to the power beta 0 plus beta 1 xi divided by 1 plus e to the power beta 0 plus beta 1 xi. This is the form that we get it here. If you look at this, exactly what we get it here, the same thing. From these conditions here, we know that logit of pi is beta 0 plus beta 1 xi, so I say that ln pi divided by 1 minus pi is this one. Then this one, if we take the log in both sides, so log cancels and e to the power, this one will be e to the power this. And then we just multiply this by this and we get this one, and then we just take the common and then we get this one. So I will just stop here. I just showed you how to get this form, why you take the logit. In the next class I will do the whole data analysis and I will bring some more examples of this, and hopefully over the weekend I will upload the homework 4. So your homework will be due in the next month. Any questions? Okay, so if you don't have any questions, I can end the meeting and hope to see you in the next class. Please feel free to ask me about your project report. So this one, this report I will not grade it, but I want to make sure you are using the correct methodology. So when you will submit this one, as I told you, just one page is fine with me. Just your methodology with the assumptions and why you are considering this. Okay, homework due a week from today. So it will be, I think, April 5. Yes. So you will get 1 week to do the homework, and homework will be based on not this chapter. It will be based on chapter 13 and chapter 10. So we already finished long ago, so you just need to review this part, and there will be like 2 data set for each of this chapter. Okay, now if you have any questions about the project, how to write the draft report, it is just either 1 page as I told you, or maximum 2 pages, but I don't think that you need to write 2 pages. 1 page is fine. You have to write your methodologies based on your research questions and which predictors you are considering and why you are considering this methodology. This is the detailed explanation should be in one page. No data analysis. And this part, I just want to make sure you are in the right directions. And then if I say that, okay, this is the right direction, go and start, do the analysis and everything, writing the reports, and then you should be fine. Okay. If you don't have any questions, then I can stop recording here, and have a nice weekend for everyone.